Okay, we are back and we are going to talk about the extreme value theorem. If f is continuous on a closed interval AB, then f has both a maximum value and a minimum value on the interval AB. So basically this is guaranteeing that there exists an extreme value on a closed interval. And this is what I was talking about earlier when I said that we were going to have something that was going to be a little bit different when it was on a closed interval. So when we look at this problem right here, it is a continuous function on a closed interval, and this would be something where you could guarantee that there is an extreme absolute max and absolute min, and we said that this was our absolute max and that this was our absolute min. And then up here, this is another function that is continuous on a closed interval. And I just wanted to point out, we had said that this was our absolute max, or absolute min, excuse me, and that this one was our absolute max. Now, had one of our endpoints been the absolute highest or absolute lowest, we could use an endpoint, okay? So you do need to consider these endpoints, but since they were not the absolute minimum or the absolute maximum, we did not include them at all, okay? And you have to remember that you cannot have a relative or local extrema on an endpoint, okay? So you cannot have a local extrema on an endpoint. So remember that this is an existence and this is an if-then statement. So if f is continuous on a closed interval AB, then f has both a maximum value and a minimum value on that interval, okay? So there's our if-then statement. So look at our example number 4. For each graph below, explicitly state where the hypothesis of the extreme value theorem fails on the interval from 0 to 3. Then determine if the function has an extrema on the interval. So the first thing that we have to look at is it continuous on the closed interval 0, 3? Well, I'm looking from 0 to 3, and I see I have a jump discontinuity at x equals 1. So I would say that the extreme value theorem does not apply. Because f is not continuous at x equals 1. And 1 is between 0 and 3. Then it says determine if the function has an extrema on the interval. Well, I mean, you're going to see that it has an absolute max of 4 at x equals 1, and it has an absolute min of, let's say, about 1/2 at x equals 0. So there's your extrema. So, you can still have extrema, but you can't use the extreme value theorem if it's not continuous on that closed interval. Part B, we're looking from 0 to 3. I see a jump discontinuity at 1.5. So therefore, the extreme value theorem does not apply. Because f is not continuous at x equals 1.5. and 1.5 lies between 0 and 3. Do we have extreme values? Yes, we have an absolute max of 4.5, let's say, at x equals 0. Now, right here, since this point right here is not a closed circle, this is not going to be no absolute min, okay, because it's an open circle. Okay, so no absolute min. Sorry about that. Okay, and let's look at C. From 0 to 3, we have a problem because it needs to be continuous on the closed interval, and notice that the closed interval 0, 3, we do not have continuity at 3, and we also do not have continuity at 0. So this is actually continuous on the open interval from 0 to 3, therefore you cannot use the extreme value theorem. So extreme value theorem does not apply. Because f is not continuous on a closed interval. Okay, so that's the reason. And if you notice, like this looks like the highest point, but it has an open circle. So there's going to be, no absolute maximum there because of that open circle. And then it goes down to negative infinity. So there's going to be no absolute min because it just keeps going down to negative infinity. So there's going to be no extrema for this one. All right, 0 to 3 for the extreme value theorem. Notice that at 0 we don't have a closed circle, closed dot, and at 3 we don't have a closed dot. So again, we are not going to be able to use the extreme value theorem because it's not on a closed interval. We don't have to worry about differentiability on the extreme value theorem because it doesn't talk about that. It is just the continuity piece. So we're going to say the extreme value theorem does not apply because f is not continuous on a closed interval. For this one, though, it does have the absolute max of, I don't know, I'm going to say approximately 4 at x equals 1, and it has an absolute min of -1, let's say, at x equals 2. So it does have, this one does have extrema, even though the extreme value theorem, again, did not apply. So the extreme value theorem gives us the knowledge of when extrema occur, but how we will find them algebraically when given an equation only without the benefit of a graph. So our next question should be, how can we identify all the values of x where extreme values occur? So for example number 5, for each function shown below, justify or explain why the extreme value theorem can be applied or why it does not apply on the given interval. Okay, so on this first one, letter A, we have to think about on the interval from -4 to 4, do I have a discontinuity? And I notice that I'm going to have a vertical asymptote here at x equals 2. And 2 is in this interval. So we do have a discontinuity here. So we're going to say that the extreme value theorem does not apply f of x on negative 4, 4, because f is not continuous at x equals 2, which is contained in the interval. And then we look at the next one, and I know that this exponential function is continuous for all x. And so when I look at it from negative 5 to 5, I think, okay, this one looks fine. I would say that g of x is continuous for all reals. So the EVT applies. For g of x on that closed interval from negative 5 to 5. That means that they guarantee that there will be an absolute max and an absolute min for this function from in between negative 5 and 5. Now, it may be the endpoints, right? That's when we have to worry about those endpoints. Okay, so C. Think about what your domain is here. You know that x plus 2 has to be greater than or equal to 0, so x has to be greater than or equal to negative 2. And so they're on an interval where, like, negative 6, negative 5, negative 4, negative 3, none of those are in the domain of the function. So we are going to have a problem. There's not going to be continuity. So we're going to say since h of x is continuous, I should say only for values x greater than or equal to negative 2, the EVT does not apply. For h of x on that closed interval from negative 6 to 6. Okay? All right. So that leads us to definition of a critical number. So a critical number of a function f is an x value, x equals c, in the domain of f such that either f prime of c is 0 or f prime of c does not exist. If x equals c is a critical value, then c comma f of c is called a critical point. So theorems, relative local extrema can only occur at a critical value on an open interval. Absolute global extrema must occur at a critical number or at an endpoint of an interval. So using the candidates test to determine absolute global extrema. Now we need to put these ideas together with a little direct practice. Let's develop an algebraic approach to what will be called the candidates test for finding extrema. Okay, so critical numbers are where the derivative is 0 or where the derivative does not exist. Very important, okay? And the point, that x value, comma, that y value for that function, that's called a critical point. And it's going to be maxes and mins and all kinds of things. So find the absolute extrema of the function on the given interval provided the EVT is applicable. If it is not, justify why. Well, I've got a cubic function that is continuous for all reals. So I know I have continuity, and this is on a closed interval. So I know that the extreme value theorem guarantees that there will be an absolute max and an absolute min. So they're asking us to find those absolute extrema on that interval. So I'm going to do that. And so we've got our values, and here's our candidates test. that they were talking about. We want to use the derivative to find critical numbers. So we've got 24x squared minus 6x minus 9. And we're going to set that equal to 0. So I'm going to factor a 3 out. I'm left with 8x squared minus 2x minus 3. I'm going to factor. I'm going to try 4x and 2x. And if I put the 3 here and the 1 here, and I've got a 6 and a 4, and so my 6 needs to be negative and my 4 needs to be positive. And so now I can see that my derivative is 0 at x equals 3/4 and at x equals negative 1/2. So x equals 3/4, x equals negative 1/2. We also need to check our endpoints. Okay, so these are our candidates. We were looking for where our derivative was 0 or undefined, and we're looking at our endpoints. So now we're going to look at what the values are of the function at these points. So we're basically just taking 3/4 and putting it into our function right here, our original function, and seeing what we get. So I'm going to just use my calculator and put this function in y1 and then look at 3/4, and I'm getting negative 3.063 roughly. At negative 1/2, I'm getting 4.75. At negative 1, I'm getting 0. At 2, I'm getting 36. Okay, so these are the candidates, and now I'm looking for absolutes. So what is my absolute lowest? Here is my absolute lowest. This is going to be my absolute min because it's the lowest y value. And then here is my absolute max because it is going to be my highest y value. 36 is the highest, negative 3.063 is the lowest. So I would say for this problem, and I'm going to go ahead and change colors because I ran out of space. We have an absolute min value of negative 3.063 at x equals 3/4. We have an absolute maximum value of 36 at x equals 2. So we're going to do the same thing on the next one. What are our candidates? Well, we're going to take the derivative. 1 minus 2 cosine x. We're going to set it equal to 0. I'm going to bring the negative over here and then divide by 2 on both sides. So I am looking for in between 0 and 2 pi, where is my cosine? Positive 1/2. Well, my cosine is positive in the first quadrant and the fourth quadrant, and I would be looking for adjacent over hypotenuse to be 1/2. So this is going to be square root of 3. This is going to be a 60-degree angle, also known as pi over 3. And then this one, there's going to be a negative square root of 3 here. This is another 60-degree angle. Only if we went all the way around, because we said that this first one was pi over 3, so we got 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. We've got 5 pi over 3. So this is happening at pi over 3 and 5 pi over 3. So where is the cosine of x equal to 1/2? That would be at x equals pi over 3 and 5 pi over 3. So those are two of our candidates, and our endpoints are also our candidates here. So x equals pi over 3, x equals 5 pi over 3, x equals 0, and x equals 2 pi. Those are all the things that we have to look at. And we're going to be using our original function to find out what those y values are, and then decide which one's the highest, which one's the lowest. This function, by the way, sorry, I forgot to mention that. This function is continuous for all reals, okay? It's a trig function, and regular sine, cosine, tangent, they're all continuous for all reals. Okay, so if I put x equals pi over 3 in, again, I'm going to use my calculator. I'm going to be in radians, and at pi over 3, I get negative 0.685. At 5 pi over 3, I get 6.968. At 0, I get 0. And at 2 pi, I get 6.283. So I can see that this is going to be my absolute min, and 6.9 is going to be my absolute max. And so I'm going to use a different color again. Because I ran out of space again. I have an absolute min value of negative 0.685 at x equals pi over 3. And I have an absolute max. Remember that the extreme value theorem guaranteed that you would have extremes, an absolute min and an absolute max on that closed interval. So an absolute max value of 6.968 at x equals 5 pi over 3. We could do exact, we could say, you know, for this one approximately, right? Because I was using my decimals. All right. So now, how about red? Okay, we've got another trig function. This function is continuous for all reals. I'm looking on the closed interval from 0 to 3 pi over 2. I want to first find my derivative. And so I would be bringing my 2 down, times sine of x to the 1, and then times the derivative of sine. And then minus a minus sign would be plus sine, because the derivative of cosine is negative sine times that negative is positive sine. And I'm going to set it equal to 0, and this is nice because I can factor out my sine, and then I'm looking for what makes my sine 0, and I'm looking for what makes 2 cosine x plus 1 equal 0, which is what is 2 cosine x equal negative 1, which is cosine x equals negative 1/2. So I'm looking for those x's. Well, I know that the sine is 0 at x equals 0 and pi. Which one is in my, are they both in my closed interval? 0 is and pi is, right? Because we're talking about from 0 all the way around to 3 pi over 2. So 0 is here, pi is here. So yeah, they're both in there. So 0 and pi are critical numbers. And then I would be looking at where the cosine is negative. And the cosine is negative in the second and third quadrant. And this would be negative 1 over 2. This would be a square root of 3. This would be a negative square root of 3. But this angle is 60 degrees. So this is going to be 2 pi over 3. So x equals 2 pi over 3. And then if I go, there's 3 pi over 3 and 4 pi over 3. So for this one, I'm really running out of space because my candidates test is down here in D. So x equals 0 is my endpoint and it's my critical number. So that one's fine. I'm going to go ahead and start here and then go around. My next one would be 2 pi over 3, then pi, then 4 pi over 3, and then finally that 3 pi over 2, which is the end. So candidates test gives me all these critical values, critical numbers. So now I go back to my original function h of x and I put a 0 in and I get -1. Go back to my original function, put 2 pi over 3 in, and I'm going to get 1.25. Excuse me. Put pi in, I get 1. Put 4 pi over 3, I get 1.25. Put 3 pi over 2 in, I get 1. So this is going to be on my closed interval. This is going to be my absolute min. And then we have a tie for absolute max. It's happening in 2 spots. So I'm going to change my color here. Purple. And so for B, that was B. We are on C right now. I'm going to say that we have an absolute min value of -1 at x equals 0. And I hate not having room to write. Absolute max value of 1.25 at x equals 2 pi over 3 and x equals 4 pi over 3. Sorry that I'm running into everything. Oops. And okay, you can't even read that. Okay. All right, I'm going to stop here and I'll pick up the rest of it on the